Here, we've got two, I think, very interesting papers coming up. I'm looking forward to them. We're going to be hearing from Steve Whitworth, Manager, Environmental Services, Ameren, who's going to be talking about managing uncertainty, a utility perspective on compliance and environmental regulations. Welcome.
Okay. Good afternoon. Thank you very much for sticking around for this. I kind of feel like the free entertainment at happy hour, but no drinks. I guess those are on your own. I just want to talk a little bit this afternoon about some of the things that we've done, an introduction on Ameren. All right, we'll do it this way. There we go. Ameren overview, so discussion about some of the new regulations that we're facing, an evaluation of some compliance strategies and the methodologies that we've used to address some contingencies, so discussion briefly about some of the options that we have as well as compliance measurement options, and then some thoughts on managing the uncertainty and being adaptable to some of the things that we have to deal with and respond on a more quick basis than the industry has typically been able to do. So Ameren, about 3 million customers overall. We have both natural gas and electric customers in Illinois and Missouri. We have several different business segments. So we have a non-rate regulated business, Ameren Energy Resources, that has generation in Illinois. We have Ameren Illinois, which is just a regulated transmission and distribution natural gas company in Illinois. We have Ameren Missouri, which is a vertically integrated utility with generation and energy delivery in Missouri. Ameren Services, who I work for, is a business and corporate services, so environmental services, HR, legal, and so forth. And we provide services to all the different business segments. And then most recently established a couple of years ago a transmission company focusing on regional transmission opportunities. So there's our footprint. We have 11 coal-fired plants, about 32 units. We have 17 oil-fired facilities, or gas-fired CTs, a couple of with oil-fired capacity, and about 51 CTs. 2 of those are combined cycle. We repowered a 50s vintage coal plant about 10 years ago to natural gas combined cycle. We have a nuclear plant, Callaway. We have pump storage at Tom Sauk. We have some run-of-the-river hydro up at Keokuk, and then also Lake of the Ozarks hydro as well. From our coal plant forecast, we've kind of bottomed out, I guess, as far as SO2 and NOx at this point in time. So overall, you've seen these typical slides of reductions, but benchmarking back to the Clean Air Act amendments of 1990, we've reduced SO2 and NOx by over 85% across the fleet. At the same time, coal burn has gone up and kind of peaked out in 2006, as most of you probably have those types of profiles, and then kind of leveled out. We're predominantly PRB coal now on all these units. From a control technology perspective, we've installed quite a bit of SO2 control. So we've retrofitted SO2 controls at 5 units, 2 at Coffeen, 1 at Duck Creek, and 2 at Sioux, and those are all Hitachi absorbers. And then we have 2 Avatec units under construction at Newton. SCR on 4 units that are originally built for seasonal operation with the NOx SIP call on the Illinois units, and then going on to annual operation under CARE. A lot of low NOx burners, neural nets, combustion optimization, overfire air systems, and we also have some injection systems, urea, both rich reagent injection and SNCR at Coffeen plant, or at Sioux plant rather. And then in Illinois, we've installed a number of activated carbon injection systems in 2009 to meet the Illinois mercury control requirement. So when CAMR was vacated, Illinois mercury rule prevailed, no trading. We have a control technology requirement that we opted into that's called the multi-pollutant standard that has both system SO2 and NOx rates, and then a control technology requirement through 2014, and then a 0.008 or 90% control requirement, 0.008 pounds per gigawatt hour, or a 90% control requirement that begins in 2015. So we've really been focused on the Illinois fleet on both meeting the technology requirements and more recently on trying to optimize, both minimize cost and optimize performance of those mercury control systems. And then ESPs everywhere, so no bag houses on our units yet. We've been able to get by with cold side ESPs. We've replaced a couple on existing units at Coffeen 2 and Duck Creek, done some refurbishments, and then we have some new additions planned for a couple of units at the Labadie facility in Missouri. So dealing with some of the major issues, and you've seen this is just another view of a lot of things that we're facing. A couple of these rules that are going to impact us that haven't had a lot of discussion in the last couple of days. There's still the industrial boiler MAC that's out there, so we have some aux boilers and some things that we're going to have to deal with in that case, as well as rice MAC, for example, on a bunch of, even the scrubber projects had diesel backup pumps and generation for those projects, so that impacts us. Transported pollutant rules. So as you know, we started out with the SIP call back in the early 2000 timeframe, moved on to CARE, cross-state rule, back to CARE, what's coming next. So a lot of our focus has been on kind of managing emissions allowances and opportunities as well. So that's one of the things that has changed is, with opportunities for either over-control and selling allowances or, the requirements to comply and, availability of allowances is kind of interesting. I think we just got our 2013 allowances again for CARE that were pulled off and now given back to our accounts in the last couple of days. So that's been an interesting process. The NACs are becoming a big issue. So as you know, we have a fine particulate rule that we expect a final rule here in another month. Ozone NACs continues to drop, and another proposal coming out next year, as well as the SO2 NACs. Both Illinois and Missouri have a few non-attainment areas, so both states have been working on developing attainment SIPs, and some of our units are, if they're not directly in the non-attainment area, they're adjacent and could have impacts. So a lot of other drivers to SO2 and NOx controls other than just the cross-state rule or another transport-related rule. From the other perspective with greenhouse gas regulations, as you know, we've had the reporting rule. There's been impacts on the permitting processes, as well as the proposed new source performance standards, which are likely to come out, I guess, sometime next year. And it's not just about air. I think the other part of this focus, and one of the points of discussion, is we have to look at this from a multimedia, holistic perspective. So, we have a couple of water regulations on intake structures. Really doesn't impact an air emission perspective unless you start looking at water vapor from cooling towers. If you start looking at an efficiency-based standard and you have to retrofit a cooling standard, now your heat rate has changed dramatically. You have other balance of plant considerations, as well as effluent guideline limitations that are coming and the tie to coal combustion residuals. So these waste products that you may have created by fuel additives for mercury control, lack of being able to use your ash beneficially, discharges from scrubbers and so forth. Now we're going to have additional standards and uncertainty driven by those as far as how do we now deal with the water and waste management issues that we potentially have created from the air pollution controls. So one of the things our company, and I know we've heard a couple of the presentations from a couple of the other companies as far as the approach. I think the approaches are similar. We took the approach of developing scenarios, and similar to a couple of presentations heard yesterday, we took a kind of business as usual approach. We took a point of view approach, and then we took a worst case approach and went through what we called a generation initiative. So it was an evaluation of defining what the emission limits were going to be under these scenarios, when they were going to hit, what types of control technology we could install, what those costs were, and then also looking at market conditions, so fuel prices, dispatch, what the economy was going to do, and so forth. And then the goal here was to develop a timeline and put in some decision points. One of the key points that we tried to build into this process as you're going through what essentially becomes a financial model is looking at when decision points occur and then looking at kind of the range of possibilities. Some of the things that we've learned in the last couple of years now have been adapted to that for basically, fracking natural gas prices. I don't think anybody would have predicted 3 or 4 years ago when we started looking at these studies what the impact was going to be. And we're in kind of this nexus in the industry. I've been around long enough where I was kind of at the tail end of the build-out on the coal units through the CT, build-out in the early 2000 timeframe, and now we're seeing probably one of the bigger shifts, both an opportunity in looking at the fleet, what it's going to be like 20 years down the road, as well as trying to maintain compliance and provide power. Some of the things we've talked about today, you forget, and I think a couple of the presentations this afternoon, we are still in the business to generate electricity. So all the stuff we have hanging on the back end makes life interesting. Maybe there's some ulterior markets and some alternatives that we can take advantage of. But predominantly our business is to provide relatively inexpensive and reliable electric power. One of the things as far as developing these is looking at what our options are. And a couple things was never assume and never say never kind of thing. So it was always good to challenge the results. I think over the last few years we've really gotten a dose of that. Is you really have to try to explore what the range of possibilities are going to be and then kind of assign probabilities to that. We've coordinated this with a business risk management tool and tried to quantify risk by assigning probabilities, range of costs, kind of what your mitigation focus is going to be. And this applies across the business, but certainly when we look at a business risk heat map of our risk, typically the legislative and economic and environment and climate risk are always the ones that are glowing red, whereas some of the other risks are manageable and you're keeping track of those. And also looking at continuous improvement concepts. So the initial focus of this was to provide, the board of directors and others a communication tool for what's coming and what the action plan is. But it's really served more as a now kind of a dynamic process to take a look at, okay, how can we modify this and continue to improve it? We've made some decisions on major capital investments, but at the same time, we're looking now at, okay, how do you optimize those assets? What are you going to do, 5, 10 years down the road? Developing a longer view, a point of view on technology and the economy and the environmental pieces. So it's really become more than just an environmental compliance strategy. It's really been more about, what's the business going to look like in the road, and the environment piece is just another part of that, puzzle as far as where we're going to go. Some of the control technology options that we evaluated, fuel choices, as I mentioned, we switched back in the kind of mid-90s as part of the acid rain to PRB coal. That's still our fuel of choice. However, we've evaluated natural gas repowering in a few plants or co-firing and other things, and looking at those, that becomes a different evaluation today than it did 5 years ago. Evaluated wet and dry FGD. We ended up choosing on all of the systems that we've retrofitted so far to go with wet FGD, mainly from a fuel diversity, opportunity perspective, and also looking at additional controls. Sorbent injection also as an option. We've evaluated, DSI in a couple cases, and haven't deemed that fits our fleet at this point in time, but still trying to kick the tires on all these technologies. From NOx, traditional low NOx burner, over-fire air systems, combustion optimization, neural nets, use of subbituminous coal for a NOx reduction perspective. Particulate, so far as I mentioned, we've tried to avoid fabric filters from both the capital and the O&M cost perspective, and the fleet is all equipped with ESPs. Almost our entire fleet was originally retrofitted with ESPs in kind of the early 70s, and then there are probably about 5 or 6 units that were actually designed with ESPs up front. But, we started with retrofits, and so that's kind of continued even at this point in time. Flue gas conditioning agents, so as part of the SO2, drop from PRB coal and resistivity in ash, we've used several different flue gas conditioning agents and are looking at alternatives. I put fabric filters on there as an option, but as I mentioned, we haven't been able or haven't had to go to that step yet. Acid gases, fuel choices, obviously wet and dry FGD and sorbent injection. And mercury, one of the things that we've really worked on hard is from an O&M cost perspective is trying to minimize the amount of carbon that we're injecting in our boilers. So, there was a requirement in Illinois if you're burning subbituminous coal, you had to inject 5 pounds of carbon per million ACF gas flow. And so we've worked to try to get some alternatives where we can do a fuel additive and minimize the amount of carbon that we're injecting, and then getting to the point where we have to meet that emission limitation. And some of that work will be used to evaluate for our Missouri fleet what we do for control under the MATS rule as well. Multi-pollutant technologies, and we've had a lot of discussion about CO2 today. So we've kind of taken an approach looking at several options on CO2, but it really hasn't been a driver so far as what we're doing, other than maybe a longer view of, is this unit viable? And when you get into selections about making changes to your fleet, one of the things I didn't put on here was, retirement. So we did shutter 2 coal plants at the beginning of this year in Illinois in our fleet. So somewhere in the neighborhood of about 500 megawatts at 2 facilities. And I heard the term deactivation yesterday. We used the term shuttered, so we still have active permits, but at this point in time, we're not operating those units as part of a control strategy to help meet that Illinois multi-pollutant standard, as well as looking at, really is it worth retrofitting those units for MATS, for these other rules that are coming. Another big issue, and I think part of the timing of this, is compliance measurements. And we've heard a couple presentations about this yesterday about mercury and the variability in mercury. And I'd like to, expand that concept that we're also looking at particulate and HCl. So as we get pushed to continuously monitor emissions from all of these facilities, and the technology that you're using to measure that, it becomes your bright line with compliance. From a utility perspective, we do have to comply, and we strive to comply with the regulations, and you have to have some compliance margin, so you can't just be at the edge. And you have to kind of balance that approach between what is compliance, what's the variability going to be, and what's the margin. So as part of this time frame, it's not only time to design and install the controls, it's time to ensure that they're going to operate to the levels and meet your expectations, and that the design, even though design could be good, the actual conditions, it's kind of like the statement on your fuel mileage on the car, actual conditions may or will vary. So we spent a lot of time working on, doing continuous monitoring, for example, installing some PM sims to test drive the technology, try to find out what that day-to-day variability is. Same thing with mercury sims and sorbent traps. Looking at one of the big challenges for the industry, we think we can get there with PRB coal from an HCl perspective, but can we accurately measure? And at this point in time, there's question as far as whether the technology really is there to make these low-level measurements. Evaluating emissions testing as an alternative, and I think that's going to be a bridge for a lot of us to actually, you're going to have to do those test methods to basically certify and qualify your measurement techniques, but at the same time, it could be an alternative for testing, but we're going to be doing a lot more testing from a compliance perspective than we have in the past. And then there's work practice standards for organics. And we haven't really talked about that too much, and from a boiler performance perspective, that's one of the items that's really gotten a lot of discussion in our shop, especially from the performance engineers that are going to have to try to deal with this and mesh this up with their outage schedules. How do you really quantify what the requirements are going to be? How often do you have to do your inspections? What the scope of those measurements are going to be? And then really, how do you set what that standard is going to be? So that's something that's really not talked about too much, and it's not a numerical standard, but it could have some impacts that we haven't really seen at this point in time. And then also evaluating plant averaging. So one of our schemes is to potentially average at some plants where we have multiple units. You still have to be able to control to the level to adapt to outage schedules and unforeseen outages and so forth, but there are opportunities under the rule, under the plant averaging. And then can you get low enough to meet the low emitting emission unit requirement and exemption under the MATS rule? So kind of boiling it down, we've kind of looked at it from a risk management perspective, by identifying the alternatives, really trying to quantify the impacts, And I think a lot of the discussion we've had in the last couple of days, there's still a lot of uncertainty. So we've had several discussions in some of the roundtables I participated in today about, is the data that we have really good? The concept of, we're running a chemical plant now in the back end, and what challenges and opportunities that brings to the table. Really trying to look at balance of plant, water and waste management, as well as impacts on performance of the unit. And then the other piece is planning for flexibility. So, just when you think you've got a rule, either it gets challenged or it will get challenged. The court is, may, leave it in place, it may not, but we can't wait for that decision to plan for compliance. So how do we set ourselves up to be able to adapt to those different situations and essentially kind of a hedge type philosophy to allow you to, react to this changing landscape. One of the key points was communication, both internally amongst our organization between, corporate planning and the financial folks and legal and power ops and the pressure or the project people, but also with our stakeholders. So we've had, a lot of discussions with the state regulatory, the public service commissions, with the environmental protection agencies in both states, and try to make, as far as legislatures and customers, so people understand all these things that we're facing and trying to boil it down in simple terms. And kind of the take home to this is, as I mentioned before, never say never. It's a dynamic process. We've always got to challenge ourselves and question what may happen, and not just assume that we really think it's not going to do this. We kind of have to set these bookends and these error bands and operate within that tolerance, but at the same time be open to be able to adapt to those conditions on a pretty rapid basis. And that sums up my presentation. Thank you.
Thank you. Questions?
Steve, on that, on Illinois, just curious, did they give you a mercury number, or they just tell you to inject 5 pounds?
You had an option, and initially it was 90% control from the mercury in the coal, or output-based limitation, 0.008. Then we worked on this multi-pollutant compliance option that gave you more time to meet the numerical limitation in exchange for fleet SO2 and NOx limits earlier. So it was a phase-in on controls and allowed us time to kind of tune those controls, see if they were going to work. When this rule was first promulgated back in the 2006 time frame, we didn't think at that point in time that we could, and we were right, especially with SO3 conditioning and bituminous or subbituminous coal in our units, that we couldn't get to that 90% control requirement by 2009. So the MPS was kind of an off-ramp and a different compliance option for meeting that requirement.
Have you looked at HCl pre-scrubber? That's very common practice in Europe. It also takes care of mercury.
I'm not familiar if we have looked at that or not, but from our fleet, predominantly the units that are burning any bituminous coal are scrubbed now, and we plan to use the SO2 alternative emission limit to meet the acid gases. On the rest of our fleet, we've done testing and evaluated coal supplies, and we're predominantly PRB, so we're really not, the focus on HCl for us has not been control technology. It's been more about measurement.
Thank you.
Question back there?
One of the balance of plant issues that I've been concerned about is when we do these fuel switches, sometimes we're using fuels the unit wasn't necessarily designed to burn, and it can be harder on the unit. So is your balance of plant analysis including consideration that it might reduce the life of the unit?
Yeah, and most of the fuel switches for us were done, kind of in the 90s, so it was an evaluation over time. And certainly there have been some, adaptations on a consistent basis and trying to learn how to burn that fuel. So, we made an effort, I guess, going back, almost 20 years now as far as switching to PRB, and those considerations have been made. And, I think some of the things are, you have different flue gas temperatures, so how does that impact your pollution control equipment, ash resistivity? It's most recently it's involved, where do you inject carbon to take advantage of, good contact time and looking at that temperature range and those sorts of things. But from the other perspective, I guess, that we've more recently analyzed from a fuel switching perspective is going from coal to natural gas on a unit. And that certainly has some, potential impacts on, unit, whether it was designed for that or not.
Other questions? Thank you very much.
All right, thank you very much.
Okay, we're getting to the tail end. We're going to hear from Robert Treadle, Vice President of Business Development, Neumann Systems Group, who will talk, his title of his talk is Turning the Tables on SO2 Economics. Okay, there you go.
Well, Steve, if you were the opening act for the bar, I guess that, no, I don't want to go there. Thanks for hanging around and staying with us throughout this week. I know we've heard a lot of discussion on the impact of gas, the impact of regulations. I'd like to give you a little bit less uncertainty today and see if I can offer you some technical advances that reduce the cost of desulfurization. I'm going to talk to you about NeuStream today. And this is supposed to work, right?
You don't want to hit the buttons if that doesn't work.
You may want to, yeah. Okay. So I'm going to skip the part about natural gas because you've heard about it to the ends of the earth today and yesterday. Talk about a technical comparison about available sulfur dioxide control technologies, including the NeuStream S system. It's an advanced dual alkali wet FGD system. But unlike our friends from Canada, we don't build it bigger. We're actually going to show you something that's smaller and a little bit cheaper. And then give you several cost studies that compare all the technologies so that you can have an apples-to-apples comparison. When we started in this business about 4 years ago, the original vision looked something like this. Apply the best from DoD-derived liquid gas contactor technology, apply good systems engineering, and result in not a 200-foot tall SO2 scrubber, but one that looks about as big as that 6-foot-tall operator there. And the idea, the vision 4 years ago was to build a scrubber that was 1/10 the volume, much less water usage, much less parasitic power by applying the best chemistries, the best physics, the best systems engineering, instead of being tied to any particular technology, which should result in a 50% savings on CapEx and a similar savings on OpEx. So as we've proven as we moved through this development system in the last 4 years, it is indeed possible. What you can see here is the relative sizes of the NeuStream system, kind of in the teal there, as a desulfurization system on a 227 megawatt PRB burning 2-boiler system, and compare that with a conventional dry scrubber. Cost comparisons are here. What we've done is built the better mousetrap. We've taken the best chemistry and the most efficient gas-liquid contactor and applied it to demonstrate SO2 control that's in production today. 97% plus capture for both low and high sulfur coals. High reliability using proven technologies that use very low parasitic power, very low water consumption. And I'll show you a few test results as we've gone through this. Everybody knows dual alkali, but nobody knows dual alkali. It was around since the 80s. There were some problems that were worked out in the 80s, but it kind of went out of favor. What we're using is the aggressive atom of sodium to grab the sulfur dioxide quickly in our highly efficient wet scrubber design, in our highly efficient flat jet technology. And then swapping out with the low-cost calcium reagent on the back end, either using lime or limestone, depending on the sulfur levels, to produce gypsum as your only waste product. This is a system that can operate either or in high sulfur or low sulfur, inhibited or oxidized mode. You have to choose. We can't build you a system that will do from 0 to 5% sulfur, but depending on what your fuel mix is, we can build a system for you that will handle either or. Very low water usage and zero liquid discharge. And what you see here is the key to the technology, the Jetbox. And it scales linearly. We don't have to worry about efficiency losses. We don't have to build 200-foot tall towers as the calcium slurry folks do. If you need more gas flow, we build more scrubber boxes, and it scales up linearly. The only thing that's required for continued high performance is good gas flow through the Jetbox. And you know, I spent 28 years doing R&D in the Air Force. This kind of computational fluid dynamics isn't that hard to get right. We can do it today. We can guarantee you good flow through the Jetbox and give a uniform flue gas distribution that gives you great capture. When you think of the sizes that are involved here compared to what conventional wet FGD asks you to do, you see immediately some savings that can come. Much less manufacturing of the working components. Smaller footprints, smaller sizes of hardware, and just everything scales down. Parasitic power, if you're not pumping your sorbent fluid 200 feet into the air, parasitic power goes down. And with some other systems engineering approaches, we've managed to reduce water usage as well. This is scaled up very quickly with our customer, Colorado Springs Utilities. This is the 20 megawatt scrubber, and to give you some scale there, that entire scrubber is about 10 feet on a side as a cube. The rest of this is ducting just to take the slipstream, but a very small footprint. It followed rigorous testing at the bench top and with slipstreams of 0.13 and 2 megawatt size. The 20 megawatt pilot was run for about 5,000 hours continuously, including 3,300 hours with the back-end sorbent processing system. So we're flowing the sodium reagent through here, taking out the sulfur, pushing it to the back end, and swapping out the sodium with calcium on the back to produce this gypsum dry byproduct. We're pretty far in Colorado Springs from the nearest drywall plant. It's a long way to Sweetwater, Texas. So this is a landfill product in Colorado Springs. If you're fortunate enough to be next to a drywall plant, this is drywall quality gypsum. The SOx removal was demonstrated at various removal levels as shown there with the pH range that's also shown there. And then we had the fortune of EPRI studying our project and issuing a report. I'm not an EPRI member, NSG's not an EPRI member, so I can't give you this report, but if you're an EPRI member, you can get it. And if you know Chuck Dean, then you understand that he doesn't pass out compliments very easily, but he said there are no barriers to scaling up. This resulted in the Colorado SIP being revised from being specific for lime spray dryers to include the Neumann Systems Group technology as well. We've also demonstrated this on higher sulfur coals on an eastern power plant in Pennsylvania, demonstrated also very high sulfur dioxide removal rates and the acid gas and mercury removal rates. These are all post-bag house mercury removal. So the bag house is doing most of the work. We're scrubbing post-bag house and not interfering with the natural oxidation of mercury through this. So very, very low re-emission rates. To compare with lime spray dryers, we've got some performance measures here. It's late. I'm going to give you these slides as you leave, so you don't have to go through this, but let's focus on a few. Parasitic power, half of a lime spray dryer. Wet process of NeuStream that uses half as much water as the dry process of lime spray dryer. We don't have time to go into that. It would take at least 2 beers. So, our primary consumption is in lime, and it's roughly the same amount of lime consumption as a lime spray dryer. There's a little bit of trona makeup on the back end because we lose a little bit of the sodium out with the dry cake, but it's a small requirement for that. One of the interesting systems engineering improvements we've made on the dual alkali system is an active heat management system, and that leads very, very strongly to the low water usage. We take the heat out on the front end, don't flash off so much of our liquid, and then reheat on the back end so that we don't have problems with acid gases condensing in the stack. No problem with the fly ash as well. The gypsum comes out as a saleable byproduct or a landfillable byproduct. This is the Drake system that we see in Colorado Springs. This is the epitome of the constrained space. We've got a interstate highway that wraps on 2 sides and a downtown for a city of 500,000 that wraps on the other 2 sides. When Colorado Springs Utilities first looked at other alternatives for flue gas desulfurization, they just wouldn't fit. So if we look at the model of it, you see where the two capture scrubber systems fit in for Drake 6 and for Drake 7, 2 boilers, and then a single sorbent processing building to make the gypsum and recycle the sodium. Compared with other flue gas desulfurization technologies, we've got some numbers up here. Most impressive is the 10x reduction in volume compared to wet FGD. Much lower parasitic power usage, about 4 times lower water usage, and the ability to do most of the fabrication off-site. The Jetboxes are built in our factory, and they're so small that for a 200 megawatt system, they would easily fit in this room and not go above the height where you're standing. So small hardware, truckable from the factory, so assembly on site is a much easier, faster operation. We've got one customer in the Midwest who's faced with 2% unemployment in their neighborhood. Now, I don't live in a state with 2% unemployment, so it's hard for me to understand what that's like. But finding qualified construction workers in some parts of this country is still a difficult task. So zero liquid discharge versus a liquid waste stream with conventional wet FGD. When we look at dry sorbent injection, the picture changes somewhat. Here with the NeuStream, we're looking at a much higher maximum performance level if that's what you need. Good removal of the oxidized mercury versus impairment of mercury removal with DSI. DSI can overcome that with the addition of activated carbon injection, of course. We've also got a very high reliability system. We're spraying a clear sodium liquor in our scrubber. We don't have clogging, we don't have pluggage. It's not a problem that affects this system. And as we talked about before, low water usage versus no water usage for DSI. A lot more comparisons to go through, but it's late and I'm going to skip to the end. What I'd like to do is show you a few cost studies of the comparative technologies. And the next 4 charts are going to have basically the same structure as this one, so we'll take a little bit of time and walk you through this one. Annualized cost in dollars per megawatt hour scrubbed versus the remaining useful life of the plant. And then we've got the competing technologies coded out here. NeuStream is always blue, DSI is always red, and then the pink band that you observe is a spread on the trona cost from $150 per ton to $300 per ton, with the red line at today's price of $180 per ton. So you see for a smaller unit with a pretty high dispatch capacity, burning PRB coal and taking out 82%, what the costs look like. And here it's very much a combination, a competition between DSI and NeuStream. And at about 9 years, you see a break even. If you're operating for a longer time, if you're dealing with a higher dispatch rate, or if you have a higher plant size, then this difference becomes greater. If you raise the removal rate on that same plant with the same sulfur to 97% removal, then the DSI drops out because it just can't make that kind of removal rate. And the competition becomes between NeuStream and circulating fluidized bed in the dashed yellow line. Over 30 years of operation with this sort of plant, we're talking about over $100 million in combined levelized cost savings. So that's a combination of CapEx and OpEx. When you go to a larger plant, again with moderately higher sulfur coal, you see this sort of competition. It gets much closer, but the low-cost option again turns out to be NeuStream, and it breaks even with DSI after just 5 years. So it's always do you buy your car or do you lease your car? Do you want to pay me now or do you want to pay me later? And it really depends on your individual case what's going to make the most sense for you. So, you know, if you're going to limp a plant through for the next 5 years with a 30% dispatch rate, then there's a clear best option for you, and it's not my product. So we'd be happy to run our cost models for your particular case and give you some demonstration of what we believe the costs to be. These costs for the competing systems come from the EPA model that Sargent and Lundy has published, and our costs are our internal numbers based on our own construction of the Colorado Springs Utilities plant and estimates on other size plants. If you go to higher sulfur eastern coal, there's really fewer options. We didn't have a good cost model for circulating fluidized bed for this one, so it's not listed, not because it doesn't compete, but because I don't have a cost model for it. But you see the NeuStream with substantial savings over conventional wet FGD at all remaining lives. So for a very high 5-pound sulfur content, then the NeuStream is very, very competitive in this case. So it's the last one, it's the last chart. You get to go home and catch your airplane. My experience with 28 years of active duty in the Air Force, catch the airplane from behind, don't step in front of it. You'll be in a lot better shape. We've demonstrated high capture from PRB and from high sulfur coal. We've got a high reliability with an adaptation of several proven technologies. NeuStream gives you low parasitic power, low water consumption, zero liquid discharge, and the ability to handle high sulfur excursions. We've got validated performance. We're producing our first commercial scale installation right now. And given the right conditions, we can save you some money. So I'll open it up for questions now, and I thank you for your attention.
I'm going to ask a question. It turns out we looked at dual alkali systems back in the 70s, sodium systems no less, and we found a very serious problem with oxidation of the sulfite to sulfate, requiring a lot of makeup. Could you talk about that a little bit?
Well, I'm not a chemist, but I have one in the audience, so Jake,
Okay.
if I get this wrong, stand up for me. What we found is you can't swap out in the middle. You have to either be fully in sulfate mode or fully in sulfite mode. And we oxidize with low sulfur coals to stay fully in sulfate mode, and we inhibit that reaction for higher sulfur coals to stay fully in sulfite mode. It's kind of like anything else. You've got to make a decision. Which one do you want to be on? And there's a tipping point. We can tweak that tipping point depending on your fuel requirements, but it's something to be avoided to be in the middle. You don't want to be in mixed mode.
Okay. I assume that impacts your sodium makeup if you're in the middle. Is that correct?
It's just a bad place to be. Sodium makeup in the middle. Jake, do you want to comment on that?
One of the things you can do is do a cake wash that recovers some of the sodium. That helps, and there's been significant advancements in the late 80s on the sulfur chemistry for the makeup of the inhibition reaction that help with those makeup costs and bring those down a lot.
Okay, thank you. Other questions, comments? Thank you very much.
They're tired. They're ready to go home.
They're ready to catch their plane. Let me close up shop now, if I could. Let me thank all of our presenters for the day. Let's give them one last round of applause. Thank you very much for the audience participation, and have a good trip back home. Thank you very much.